Today we will discuss a very interesting and important concept in air transportation called as the wind-rose diagram. The wind-rose diagram is a very important requirement whenever an airport is planned at a new location. Now, the content of this particular session has been created by two interns. First by Kuldeep Namdev, who was at that time in the Department of Mechanical Engineering at NIT Rourkela. Subsequently, he has gone to UIUC. And recently, the contents were updated by Yash Kapsikar, also from Department of Mechanical Engineering at DJ Sanghvi College of Engineering in Mumbai. He has been a topper of one of my NPTEL courses, and hence he is associated with me as an intern, and he is helping me in creating and improving the content for this new course. Here are images of two major airports of India. The first on your left is VIDP and the one on the right is VABB. These are the names given by ICAO. You must have guessed that the one on the left is the airport at New Delhi, the Indira Gandhi International Airport, IGIA, and the one on the right is the Chhatrapati Shivaji Maharaj International Airport in Mumbai. Also notice that the airport at New Delhi has two parallel runways and a few other runways also, and the airport in Mumbai is having two runways, but they are in a cross configuration. So, why is it so that both the airports have these two runways, but in one case they are parallel and in the other they are at an angle to each other? That is what we will learn today through the concept of wind-rose diagram. Whenever we design a new airport, there are many factors which affect the location of the runway or runways and their orientation. The most important and the fundamental factor that affects the choice of the runway orientation is the most prevailing wind direction. At some airports, the weather patterns are such that throughout the year, the wind mainly blows along one principal direction. In those cases, there is no problem. One can easily align the runway along that direction. The second consideration is the availability of the airspace at any location, because sometimes the airspace is constrained by restrictions imposed due to defense airspace or prohibited airspace, etc. So, many a times availability of the airspace can also restrict the location and the orientation of the runway. Then there are some environmental factors such as noise. Runways have to operate in the vicinity of cities, and cities have people like you and me living who are not very happy with the noise created by operation of aircraft. So, sometimes we may have to keep that in mind. Then there are constraints from air and water quality, because the effluents that are generated from an airport have to be consumed and taken care in the locality near the airport. Similarly, airports also cause a large amount of air pollution because of the engines which consume large amount of fuel. So, you may also have to orient the runways keeping in mind where these exhaust plumes are going to be located. There could be obstructions to the navigation, and hence it could affect the location of the runways. Then every airport should have a control tower where the entire airport and the entire runway configuration should ideally be visible to the air traffic controller. So, many a times the air traffic control visibility issues can also constrain the runway location and orientation. And finally, there could be hazards because of wildlife. Many airports are located in the vicinity of wildlife reserves or areas where there is a crossing of wildlife, and there could be constraints imposed because of these. Several of these are present when we choose the runway orientation, but mainly we will study today about the most prevailing wind direction as the primary factor. Let us have a look at how the runway orientation gets affected because of the presence of the winds that blow in a particular direction. Preferably, takeoff and landing of an aircraft should always be against headwind, because that gives the least takeoff distance and the least landing distance. So, this is what we would prefer, and hence you will notice that aircraft normally take off and land in the same direction, preferably against the headwind. Right? Now, whenever we have landings in tailwind direction, that means the air blowing from the rear of the aircraft towards the aircraft nose, or sideways because of crosswinds, the safety of operation is always at stake. So, for example, if you have a tailwind, then the takeoff distance will be larger and the landing distance also will be larger, because now the air is not coming opposite to the aircraft. So, the relative winds are going to be lower. And if you have crosswinds such as in the blue color, then the wind flow, if the wind flow is along the black color, then you can get crosswinds, and crosswinds are going to be a problem. In this case, we have shown a crosswind in the tailwind direction, but it also could be a crosswind in the headwind direction. Both of them are not desirable to the extent possible. Okay. So, in crosswind landings, the wind is coming at a direction alpha, and this can be resolved into two components, the headwind components or the tailwind component depending on the direction of V as V cos alpha, and then there is a crosswind component called as the V sin alpha. So, we need to be very careful that the value of V sin alpha does not exceed a particular specified value, otherwise there will be a possibility of danger during landing. Here is a photograph of an aircraft coming into land at an airport in Portugal called Madeira, which is very famous for crosswind landings. I would encourage you to look at this particular YouTube video, whose link is given in the slide below. You will see some very interesting and fascinating video clips of crosswind landing at Madeira airport, and that will give you an idea about how dangerous it can be to land an aircraft in crosswinds. So, as I mentioned, there are maximal permissible crosswinds specified both by the Federal Aviation Administration, which uses the airport reference codes to specify the allowable crosswind component. Notice that larger airports, which are A4 through D6, they normally handle larger aircraft, and hence the allowable crosswind component is much larger. A1 and B1 are airports which cater to small aircraft, and there the crosswind component permitted is very small, just 10.5, around half of that for the larger airports. ICAO uses a reference field length for categorization of permissible crosswinds. It assumes that aircraft which have a larger reference field length, 1.5 kilometers or over, they will be larger aircraft, and for them the crosswind component allowed is maximum 20 knots, and for smaller aircraft which require lesser length of runway, the reference field length being less than 1200 meters, there the crosswind component is 10 knots. So, these are the two regulatory requirements or specifications which are to be taken care when we operate an aircraft from a particular airport. So, once again, if the crosswind component is more than what the aircraft can handle and what the airport permits, then you have to go around or you have to divert the aircraft. Now, a runway is supposed to be available to allow the takeoff and landing activities at an airport almost at whenever needed, but there are certain restrictions. It's very difficult to have a situation where the runway is always available, so we define something called as a airport usability factor. So the runways are oriented at an airport to ensure that this airport usability factor or AUF is always more than 95%. What it means practically is that for 95% of the time, the runways should allow operation of the aircraft, and 5% of the times we can permit cancellation of landing or takeoff because of huge crosswinds or runway non-availability. What exactly is the airport usability factor? It is the percentage of time during which the use of runways is not restricted because of excessive crosswind component. So, in general, a runway of an airport should be available 95% of the time. If you do not have a possibility of meeting this requirement with one runway, you have to go for multiple runways. So, remember that AUF should be more than or equal to 95% with the allowable crosswind components not exceeding the limits which I have specified in the previous slide. Now, what happens if the AUF is less than 95% with single runway? As I mentioned, you have to go for cross runways. You cannot go for parallel runways because that won't help, because parallel runways have the same direction. So, if the wind is coming at a crosswind, then both runways will be of no use. But if you have cross runways, then you can incline them at angles so that the crosswind component in at least one of them is below the permissible limits. Okay, now if we want to know how the runways should be oriented, we have to follow a procedure, and that is where the windrose diagram plays a major role. So, the windrose diagram is used to find the runway or runways orientation if there is more than one runway required, and we do this by using the average meteorological data for last 10 to 15 years, sometimes even more, 20 years, because weather patterns do change over time. So, if you use data for only a small period, then you will find that by the time the airport is ready, the direction of the winds have changed, and then you have much larger crosswinds. There are broadly two types of windrose diagrams. The first type is called as type 1 diagram, where we take into consideration, based on historical data, the direction of the wind and the duration during which that wind is blowing. The type 2 diagram is more rigorous. It not only looks at the direction of the wind and the duration of the wind, but also the intensity at which the wind blows in each of these directions. So, both type 1 and type 2 windrose diagrams are used, and we will see both of them very shortly. Let us first look at how to draw the windrose diagram of the first type. So, what we do is we take a circle and we divide that into parts representing the various directions in which the wind is blowing. Usually we divide it into 16 parts. So, from north, south, east, west, we have 3 more components of each direction, like south, southwest, southwest and west, southwest. So, in order to get a more accurate data, or in order to get a more elaborate information, we divide it into 16 parts, and generally we also draw concentric rings representing various wind direction distribution, 5, 10, 15 or 20, 25 meters per second or miles per hour. The red line in this figure shows the wind direction, the direction in which the wind is blowing. Now, the circle that you see in purple color, it gives you sectors, and in each of these sectors we insert, based on the weather data, the percentage time the wind blows in that direction. Okay. So, each of these directions we will fill in now the number based on what percentage of time the wind blows in that direction. So, this is an example of the data at a particular airport plotted based on the meteorological information. So, each point in this figure represents the direction in which the wind blows, and also it represents the percentage of the time. So, for example, if you look at this point is between 5 and 10, I would say approximately 8. So, the wind blows in this direction approximately 8% of the time. The central circle represents the calm winds lower than a particular magnitude, okay. And this point, for example, the one on the bottom represents that the winds are blowing in the north-northeast direction for approximately 15 or winds of 15 units meter per second or miles per hour blow in this direction. So, then what you do is you join all these points and then you create this particular figure. You have a shaded figure that joins all these points. So, with this you get a visual indication of in which direction is the wind primarily blowing. And then the best direction in this figure is the one where you have the longest line in the figure. For example, here we have the best direction as the south-southwest. So, if I have to build an runway at this airport, I would align the runway along the red line to the extent possible with the constraints imposed by other things taken care. The windrows type 2, as I mentioned, looks not only at the wind direction and the intensity and the speed, but duration, but also the intensity. So, in the center you have a circle which has the actual wind velocity percentages. For example, all percentages or during the entire year, how many percent of the times the winds are calm below 4 mph, that percentage will be mentioned inside the inner circle. And then you have this circle, first ring circle of 15 miles per hour. So, in each of these sectors you will mention the intensity of the wind as a percentage throughout the year, and then you fill the other circle and then the next circle. Okay. So, what you do after that is that you take a transparent template. This template will be having a center line, which is the runway center line, and then there will be a permissible crosswind component C. So, the width of this template is going to be the permissible crosswind component, right. So, what you do is you just take this template over the windrows, align with the center. Now, this is one possible runway orientation. Now, what you do is you just rotate this particular template and keep on recording at which orientation you get the maximum value of the area covered below the template. Right now the template is blank, so you do not see the value of the intensities, but now here is a table of a particular airport which has recorded the data. So, out of 100% time, 8.1% are winds which are calm. By calm we mean less than 4 miles per hour. And then at various sectors, what is the true azimuth, and between 4 to 15 miles per hour, what is the percentage of time that the winds are blowing. So, it shows that in an overall sense, around 60.4% of times the winds were 15 miles per hour or between 15 and 4 miles per hour, more than 4, less than 15. Similarly, around 20% of the time the winds were between 15 to 20 miles per hour, 10% of the time they were 20 to 25 miles per hour, and only 1.6% time the winds were more than 25 and less than 35 miles per hour. So, what we do is we just start filling this circle with the data. So, first you look at this data on the right hand side, you have the calm winds 8.1% of time. So, in the central circle we write 8.1 because this circle represents the times during which the winds are calm less than 4 miles per hour. Then we look at the first column here, which shows the winds between 4 to 15 miles per hour recorded on an average over the year, and depending on the value of the sector, like north 2.4, so we put 2.4 here, and then we put 3 here and 5, so on and so forth. This way we enter all this data into the sectors here. So what we notice in this figure is that the maximum value is 7.1%, which is from east to west direction. Okay. So throughout the year, 8.1% is the calm winds and 7.1% maximum are the winds in the direction east to west, and like that there are directions given for each of them. Then we go to the outer circle. In the outer circle, the winds are to be recorded between 15 to 20 miles per hour. So 0.4 corresponds to this 0.4, 1.2 corresponds to this 1.2, and this, like that. If you go around, 0.9 corresponds to this direction, north northwest direction. Okay. So you fill the first outer circle also. Then you fill the second outer circle, where the total duration is 10.2 distributed in the following fashion. Here also we see that the maximum value is 1.9% along the east-west direction. So we already know that the east-west direction seems to be a direction where there is a lot of wind, but you can't be sure, you have to confirm this. And finally we go to the outermost circle, which has winds recorded only beyond 25 and till 35 miles per hour, very less amount, only 1.6% in the whole year. So those numbers are added here. The ones which are blank represents 0. For example, southeast is 0 because there is no wind recorded in this direction throughout the year between this particular wind band. Having done that, now we have filled the entire circle with all the data regarding the directions. Now we take the template again. Now in this particular example, the limit of crosswind is 15 miles per hour. Suppose the limit is 15 miles per hour, the width of the template will be 15 miles per hour, and when you move it there, you start calculating the area covered. So what you have to do now is, you have to start covering, you have to start adding the area which is covered below the template at various directions. So we start with the east-west direction as shown here, and these numbers like 0.2, which are fully covered under the template, are counted full. 1.7, 1.9, 1.9, 3.1, 2.3, they are all counted full. But a number like this, 1.6, okay, a number like this, if you see. So let us have a look at a number like this. Now this is 1.0, but it is only covered for a small fraction. So we need to eyeball this fraction. I would say this is approximately 40%. So this area will be approximated to as 0.4 of 1.0. Similarly, if you look at this area, this particular sector, I would say it is 30% of 1.2. Similarly, this also is 30% of 0.9. So for this particular area, you will take it as 0.3 into 0.9. Like that, the area which is completely covered like 8.1 and the inner complete circle, those numbers will be added totally, and all the others will be added. And then what you do is, you then keep rotating this template at various angles and keep calculating at what angle you have the maximum area covered. By area, I mean the addition of the numbers inside the circle which fall below the template. So in this particular example, what we do is, we just put the template at east-west direction, and we just manually look at how much is the area which is not covered outside the rectangle. So by approximation, you can check that this number is 9.2, which means the area under the template turns out to be 90.8%. Now this is the maximum value of all orientations, right? So therefore the runway that will the runway east-west, okay, that is giving you the maximum value in this particular example, and the coverage is 90.8%. However, please note, we want the coverage to be more than 95%, and here the coverage by this one particular runway aligned east to west is only 90.8%. We are short by about 4.2%. Therefore, the problem is that you cannot manage with just one runway in this airport. because the best coverage you get with the runway along east-west direction is still below 95%. So, what do we have to do is, we have to go for cross runways. We have to add one more runway. So, then to do that, what we do is, first runway which gave 90.8 coverage is finalized using the first template, and then what you do is, you rotate and find out what is the next best orientation that gives you the next best added coverage. In this example, you can verify yourself that runway oriented along 12 degrees and 192 degrees gives you maximum additional wind coverage of 6.2%. Now, here we do not include the area which is already covered in the first template. We only include the area which is covered outside this area and outside this area. Okay. So, total coverage will now be area between T1 and T2 taken only once. So, that will be 90.8 with T1 and additional 6.2, which is 97%. This number is more than 95%, so it is acceptable. Therefore, at this airport, for the given data, it is possible for us to go for a runway which is shown here. Okay. So, we need these two runways, but I mentioned that there could be restrictions on the runway orientation because of certain obstacles or certain areas not available. So, for example, assume that the area marked in red color is not available for us to build a runway for whatever reason. Let us not get into the reasons. So, then what you have to do is, you have to find the next best feasible runway. So, what we have done is, we have rotated the template slightly and we found that if you go to 0, 3, 2, 1, that is 30 degrees and 210 degrees, you get additional coverage of 5.8%. This is less than 6.2%, but 6.2% we can't use because the runway cannot be put in the red area. So, if you add this number, you get 96.6%, and that is more than 95%. So, this is acceptable. Okay. So, basically we have had a look at how runway orientations are decided, and we have also had a look at how the orientations may not be exactly matching with what you want because of certain constraints. Let us look at the actual windrows diagrams of some airports. This is the diagram of Ranchi airport. You can notice that the runway orientation that we get using the type 1 windrows diagram is roughly matching with the actual angle of 132 and 212 degrees. Then this is the Jharsuguda airport, which was built in September 2018. Here you have one runway at this orientation as per our estimate, and also matches quite well with the value of the actual runway. Okay. Then we have a Pondicherry airport, which was operationalized again in 2017. Our windrows calculations using weather data showed the runway to be oriented like this, and it also matches with what we actually have. This is Shirdi airport. Here the runway is 0927 in reality, but what we got is little bit different. Now, the reason for this is that we are not able to get land exactly aligning with that particular direction. So, therefore, we have gone for slightly changed direction. Tirupati airport, which was opened in 2015, has a single runway aligned roughly matching with what we also got. Delhi airport, it has a runway along that direction. Mumbai airport, our calculations indicate only one airport, but this is not going to give us the full coverage, because this is only giving you the prominent wind direction. So, one of the runways, the secondary runway, is matching. Note that the data that we are using in this particular diagram is not necessarily the complete data. So, I am just trying to show you that with the existing information, we are able to get the diagram roughly matching. Now, here is one apparent discrepancy. The Munich airport in Germany, as per our calculation, the runway should be oriented like this, but the figure or the photograph shows it at a different angle. Now, the reason for this is very interesting. This is not a misalignment. This seems to be a misalignment. The problem is that the direction of north is not correctly matching in that particular image. If we take a figure of the airport with north in upward direction, just like matching with the diagram, then we get a very good match between the calculated direction and the actual direction. London City Airport, now here there is no problem, both are in the north direction, but the runway orientation is quite different from what you actually see. Now there is a huge reason for this, and that reason I would like you to figure out yourself and let me know. The answer lies in the figure on the left hand side, which shows the runway of this airport. Okay. So, why we could not put it in the direction that we get by the windrows, you have to figure out an answer. Here is an interesting airport at Gibraltar. This airport is used both by road and by aircraft. So, when aircraft are operating in the runway, you can notice that the barriers are put on both sides and there is no road traffic, and this is the runway orientation, right. But when the aircraft are not flying, then the runway is open for road traffic. It is a very interesting example of a runway which is also available for the road traffic. Now, let us look at one of the busy airports in the world, Heathrow. Our estimate shows the requirement for more than one runway, and Heathrow also has got runways in more than one direction. In fact, it has got many more runways because we want to handle more traffic. Now, let us quickly look at some resources available to you to draw your own windrows diagrams. If you want to draw the type 1 windrows diagram, which is something like this, you can go to this particular website from Iowa State University, the Iowa Environmental Mesonet. There you can get data for most of the locations and the airports. For example, if you want to acquire data, you have to go to the selection of the network. In this case, we have chosen India, and then we have selected the airport called as Agartala, and if you do that, you can get the data for Agartala airport. This is the data for the Mumbai airport obtained from the same database. And then if you click on windroses, you will be able to get the windrows diagram. Similarly, you can acquire the windrows diagram for most of the airports in the world on this very lovely website. So, please note down this website and go and look at various windrows diagrams of various airports. There are also some softwares available for windrows diagram part 1. For example, if you use MS Excel, you can get a diagram like this, whereas the windrows diagram number 1 looks like this in normally it looks like that. So, there is a bit difference, and there is a tutorial available online where you are given a detailed explanation in about 8 minutes on how to make a windrows diagram in Excel. So, please watch this video at leisure and learn how to make the windrows diagram. MATLAB also has given a windrows diagram code. The one on the left is the windrows diagram obtained using MATLAB, and the one on the right is the windrows diagram for Chicago O'Hare reported from the website. So, you can see that you can draw your own windrows diagram, but remember, the data that is used for the figure on the left is not as exhaustive and extensive as the one on the right, and that is why the values may not exactly match. Okay. So, here is the type 2 windrows diagram, and here is the type 2 windrows diagram given by the MATLAB software for 20 years data. You can notice that they are very closely matching. Okay. So, that gives you confidence in the tool. There is also a freeware called as WR-Plot View, which is a trademark item. You can get a free version of this software, and you can use it to draw a windrows diagram of this particular type. Okay. So, this is also something which we would request you to try out. To acquire data for WR-Plot View, there is a website which allows you around 1000 points only. That is a huge limitation, but still it is better than nothing. So, from here you can get data for the WR plot. We have used this data for a sample airport called Jodhpur in India, VIJO. So, as per our calculations for the data that we could get 1000 points, this is how the wind orientation looks like. So, the runway should be like this, and now when we compare the information with the actual data, we find that it is roughly matching. So, here we have a picture of Google Earth showing the Jodhpur airport, and on top of that is the superimposition of the Windrose diagram that we obtained using the WR plot software. Okay. So, there is also a lot of data available about runways at various websites. One of them is this website from skyvector.com. Almost all airports in the world, you can get the data. The Airport Authority of India also gives us data under what is called as the Aeronautical Information Publication, or AIP, which they have now digitized and they have made it available as EAIP India. So, you can go to this website and you can get information about all airports in the country. They also give supplements whenever there are changes, new airports come into being, new buildings get constructed, or there are changes in the charts. The supplements are also issued by the Airport Authority of India. So, I hope with this you are able to appreciate how the number of runways required, the minimum number of runways required at an airport are decided, and once you can get the meteorological data of an airport, you will be able to also decide at what orientation the one or the multiple runways should be given. Notice that many airports have 6, 7, 8 runways. That is not because of the Windrose diagram requirement, that is because of the requirement of increased traffic. But the principal directions at which the minimum number of runways have to be built to allow operations can be given by the Windrose diagram. Thank you so much for your attention, and I hope you are now able to utilize this information to satisfy your query regarding airport orientation. Thanks.